Okay, let's start. Okay, MP6 is available. I wanted to spend a couple minutes talking about MP6. I believe that in terms of workload, the workload for MP6 is concentrated most heavily on the first half of the MP. So I think it's harder than the second half is. The first half is building the data structure that you use to build a photomosaic. The second half is actually building the photomosaic. So yeah, so I think the first part, I just be prepared. Go read it today and make sure you understand what's going on. You have everything from class that we're going to give you that you need to do it. So it's just using an array as a hierarchical structure, different than you've seen before. So you can start now. There's no mystery to it. So the implementation that you use is called a KD tree, and we're not actually going to spend time explicitly talking about KD trees in lecture here or even in labs, but you should be kind of proud of yourself that you will be exposed to and will master this data structure that other courses at higher levels in curricula treat a little more robustly. So I think that, you know, this is one of the things that we add into this course that's kind of extra, and you'll see as you do it that it's really not all that hard. And when you're doing interviews, you can go, oh yeah, I know how to do KD trees, whereas your peers at other places may not have that luxury. All right, but we're not talking about KD trees here. Our trees have a different alphabetic preliminary. We're now talking about B trees. And today we're going to spend some time justifying their efficiency for use as a data structure at all. So I have reminded you here about the definition. And this definition is really a list of characteristics, right? Like it just describes a thing kind of in English. There's nothing very little mathematical about it. So I want to reinforce some things that you should observe. It's okay. Some things that you should observe mathematically about it. All right, so refresh my memory. Here's an example B tree. Do you remember what the order of this B tree is? We talked about it. This is a B tree of order. Do you remember? 3, 4, 5, 52. It's order 5. That's right. Okay. I know it's not order 4 because in an order 4 tree, no node will contain more than 3 keys. Okay, so the maximum size is 1 less than the order. Maximum number of keys in a node is 1 less than the order. And I know it's not order 6 because if it were 6, then all of these would be in a node. So let's talk about this order relative to node size for just a second. Now in this discussion, I want you to ignore the root. The root can be any size it wants. Okay? The root can be any size it wants. We're going to ignore the root. But when you look at the rest of the tree, even in this very small superficial example, it jumps out at us that no node has fewer than that many keys. That many. Okay? That is, none of the nodes are very empty. None of the nodes are very empty. The way to think about this is that each node has capacity for, and they are actually implemented this way. Each node, each of these nodes, has capacity for, and we have things set up so that they are never very empty, and of course they can't be more than full. So that the actual number of keys is always going to be at least half of the size of the node itself. Now what this means is that every node is in a sense efficient. That is, it's holding, well, at least a factor of a half as many nodes as it possibly could. Okay? In the example of 5, it's not very compelling. But just pretend for a second that our M, our order for this tree, is 50,000. Okay? In that case, no node will hold less than about 25,000 keys. That is, each node is pretty full. Was that a bully move? I'm sorry. It's good? Okay. You can walk across here if you want. I'm sorry. Oh. So I was really just helping you. Okay. Oh, shoot. Oh. Yeah, karma. Is that what you just said? Did you just say karma? Yes, karma. All right, fine. We'll try. Oh, it thinks my machine thinks it's connected, so sorry. Okay, so where are we? So where we are is to say that, remembering that each of these nodes is intended to represent a fundamental unit of transfer across your processor, from your processor to some remote storage somewhere. Remembering that, what you realize is that every time you go out and you get one of these nodes, since they're not very empty, you're getting a bunch of data, right? You're getting enough data to compute on. Now, last time after class, somebody came up and pointed out that, you know, if we're getting all this data, couldn't we do anything we wanted to? If we're getting all this data into main memory, couldn't we do anything we wanted to do after that? And the answer is yes, 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 ding, 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 of course. Once your remote communication has completed and your data is in memory, you can build an AVL tree out of it if you want to. You can do binary search on it if you want to. You can do anything you want to on that data. You can make a hash table out of it. You can do anything you know how to do. But at that point, you're just operating on the data that's in memory. So it's sort of like all of this setup is kind of precursor to anything else we have done in the class. Okay? It's how do you pull a block of memory. Okay, any questions about that? It's all just sort of motivation and setup. All right, so I want to spend a few minutes analyzing these structures to get bounds on how many keys they hold versus how tall they are, and see if we like them analytically. So from an analytical sense, how do we feel about these data structures? Okay, so M is going to be important to our analysis. In practice, but important in a couple different ways. In practice, M is on the order of thousands. And it depends specifically on how much memory you can pull, how much memory the architecture of your machine allows you to pull at this point. So so M is a value that's going to go up as time goes on, as the actual construction of machines changes. So right now, M is kind of a big number. All right, so here's what we observe. The height of the bee tree, the tallness of it, right, the distance from the root to a leaf, determines the number of disk seeks possible in the search for any particular key. So I want to clarify pieces of this. So disk seeks are very expensive. They are the thing we want to minimize. When we say possible here, we mean worst case. Oh, all right, I'll give up. I'm sorry. I thought I had said something funny, but no. That was supposed to be a joke. All right. Me and my cell over here. Okay. All right. So the height of the bee tree determines the number of disk seeks. Those are expensive in terms of time. They take a long time. When we say possible, we mean in the worst case. So we admit that you might get lucky and search for a key that happens to live at the root. We don't even care about that fortunate circumstance. We only care what might be the worst thing that could happen to you in a search for a key, for example. And when I say search here, or when I say data, I mean a search for a key. The intention is that we would also get the value. So this M here, which reflects the size of a block, probably also includes the amount of data, the size of your value, the amount of data that you can pull as well. Okay. So we want to be able to say that the height of the structure and thus the number of disk seeks is no more than what? What goes in this blank here? What would be good news? Linear? Would linear be good news? Yeah. Okay. Log n. I assert we could go home today if this is really all that we need to show. Why? How could we go home today if this is really all that we need to prove? Why? That's right. If this is all we're after, look at how tall are AVL trees? Log n, right? No worse than 2 log n. In this case, in this analysis, the base of the logarithm actually matters. We care about it a little more than we want to. When we write our asymptotic analysis, when we write a reflection about asymptotic analysis, we will typically say big O of log n, and we don't write a base at all. Why? Why don't we ever write a base? Yeah? Base 10 is implied, really? Maybe. The question is, do we care? That's why I'm being flip here, yeah? Yeah, right. This is a high school thing, right? Logs of different bases are all just constant factors of one another. And the minute we admit that big O, we've got this magical C that we're willing to deal with any constant factor. In this analysis that we're going to do for B trees, we're still going to report things in big O of log n, but we're going to add this little m here because we care in this case that m is bigger than 2. Okay? What happens as your base grows to the function log base k of n, what happens to it? Those log functions, do they grow faster or grow slower? Yeah, grow slower. That's right. Log base 10 of a number is going to be much less than log base 2 of a number. That's right. So as m grows, these running times get slower. This is all intuition. Especially because I'm gonna lie about it a little bit, or I'm gonna I don't know, back off of it a little bit. We're gonna hold m constant. M is going to be a fixed value for these things. So we're going to argue that this is log base big O of log base m of n, where m is greater than 2. All right. M is in practice. In practice, a large constant. Okay, you're not going to like that too pretty soon, just a minute. Okay, as we saw in the case of ABL trees, finding an upper bound on the height, that is the worst case behavior of an algorithm that navigates the height, is the very same thing as finding a lower bound on the number of nodes you can throw in such a structure given its height. So what we are going to do is take H as given and analyze the lower bound on the number of keys. So a lower bound on our version of n, which represents the least number of keys. Okay, so we want this relationship between the height of the structure and the number of keys that it contains. Okay, that first sentence is just a repeat. Here's our strategy. Here's our strategy. The first thing we're going to do is count nodes. Like this is a node, this is a node, this is a node. So the first thing we're going to do is count the number of nodes. And then we're going to ask, what's the fewest number of keys we can throw into each one of those nodes? We're going to count nodes level by level. And keep in mind that we're doing a lower bound. So we want to know the least number of nodes possible, because that would be the highest height, the tallest tree. All right, what's the smallest number of nodes for the root? Number of nodes, the smallest number of nodes for the root. It's kind of a silly question. Okay, now the question is not so silly anymore. What is the smallest number of nodes in a B tree on level 1? So I'm telling you that it's a B tree, and I want to know the least number of nodes that we may have on that first level. Yeah, 2, that's right. You're recognizing that the root may have only one key and that there will be a child node on either side of that one key. So on level 1, we may have 2 keys. That is, the top of the tree might look like this. Okay? And that's 1 and then 2 nodes on level 1. Now things get interesting. How many nodes are there on level 2? And I forgot to give you a definition. So that you don't have to flip back, it will be convenient for you to let T represent this ceiling of M over 2, or the about half. So how many nodes are there on this second level, on level 2? How many nodes are there? Nodes, not keys, nodes. You see it? If you see it, sketch it down. Just write it down. You see it? I'll give you a hint. There's a factor of 2 because the same thing's happening over here as over here. So how many are there? 2 times T. That's right. That's what this characteristic tells you, right? All non-root internal nodes have between the least number is this many children and the most number is that many children. Okay, any question about that? Okay, So how about the next level? And I'll give you a hint. Each one of those nodes on level 2 has some children. How many does each one of them have? At least t. So how many in total? 2t times t. Good. 2t squared nodes on the level. Dot, dot, dot. In general, the bottom level, what's the smallest number of nodes you can have? 2 times t, I heard that part clearly. 2 times t, t2 to the h minus 1. That's right. Good. Very good. Okay, any question about that? So I want to count the total number of nodes in the whole tree, in the smallest possible tree. The total number of nodes is the sum of all of those, right? You can add them up level by level. So it's going to be 1 plus 2 times the sum from k equals 0 up to h minus 1 of t to the k. Oh boy. Major brownie point possibility. Part of this is easy. 1 plus 2. What goes there? Is that a blank? What do you call that line that divides a fraction? I don't have a name for it. Yeah? So I'm going to take the top of this. So most of what you said is absolutely right. So it's t to the, it's the top of the sum plus 1. So this would be h, right? Yeah? Is that what you actually did say that? Minus 1 over t minus 1. This is the total number of nodes. N is keys, though, not nodes. N is the number of keys. Okay? And that's what we need to count. So the least total number of keys, well, how many keys might be in the root? 1. Good. And then in each one of these other nodes, how many keys are there? Each one of those nodes has as a lower bound the same value. How many? T. Why? Why t minus 1? What's going on there? Yeah, that's the number of keys, right? The smallest number of children is t. Thus, the smallest number of keys is t minus 1. Yay! I love this moment. These are keys, least keys per node. Okay? Seriously, if this were a movie, if the whole semester were a movie, and we were like analyzing the delight in every moment of the narrative, this moment would be like whoa, I don't know, like a first kiss in a rom-com or something. Yay, we get to do that. Okay? So those t's cancel. And we have this really nice expression then for the lower bound on the number of keys. Let's see. Oh, even I can do this. It's 2 times 2 to the t to the h minus 1. Yeah? All right. So I don't care what you do with n keys. Let's see. How do I say this? Oh, no. If I tell you to build a B tree of height h, I know that if it's a valid B tree, it will have at least this many keys in it. Okay? I tell you to build one of height h, it will have at least this many keys, maybe more. All right, that's what it means for it to be a lower bound on the number of keys. Okay, so this is rewriting pieces of this. So the least total number of keys is, oh, help me remember, 2 times t to the h minus 1. But our real number of keys here is, our real number of n is really at least that, because that was the smallest number. And then we're just going to invert that. We're going to invert that expression because our disk seeks are in terms of h, right? I want to know some bounds on the height. All right, so I can do that. That's n plus 1 over 2, right? Take the log base t of that. Yeah? Did I do that right? Who knows at this point? Let me tell you. Okay, let's talk about it for just a second. So look what we have. We have h, the height, is no more than the log base some big number, right, m over 2, some big number of this fraction of n. The way I'm going to write this is h is big O of log of n, and that would not be a lie, but I want to indicate in the argument that even though m is a constant, the base of our log depends on it. It's not just any old log. It's a log that we can analyze more carefully because we know of this branching factor. Okay? Now, there's a subtlety here that you want to yell at me about, and that is the observation that t is actually less than m, right? That this function actually grows slower than, no, more quickly, sorry. This function actually grows more quickly than this one that we're talking about. But because t is dependent on m by a constant factor, we allow it. We just let it go, okay? So it's very common to relate this, the height using this expression where we kind of understand that there is a significant constant factor here, but that constant factor depends on m. Okay? All right, any questions about it? But the next thing I'm going to say is m's pretty much fixed, so it all goes out the window. It's still just big O of log of n. Okay, any questions about that analysis? So we are now happy. The number of disk seeks is only logarithmic in n in the worst case, and we can make our lives better by increasing m. All right, so, and that's it. That's really all I have to say about B-tree. So I'm going to pull it together in a summary, and then I'm going to ask you to make 2 observations. So the only pseudocode you have seen here is search, okay? So this more careful analysis depends specifically on search. We spent big O of m time per node looking for the appropriate child to explore. Okay? And the argument that we just had says that the total running time in searching for a key is m, which depends on the time that we might spend at each level. Okay? But again, consider m to be a large fixed constant. Okay, so what bugs you about this analysis? Does anything bug you about this analysis? You fine? You're just happy to move on? Is it okay? I think there are two things that might bug you a little bit. They probably bugged you before. I'm going to ask you, is that accurate, first of all? And then I'm going to ask you about this piece of it. Okay, we already mostly had that discussion. But what bugs you about the big O of M for search? What? Anybody want to raise their hand? Yeah? Yeah, this is that case where we could do binary search. We could do binary search looking for the key. So that M is really a log M if we're being super careful. Okay? And then the other one that I wanted to re-emphasize is that this one is really no different than AVL trees, like we said before. So I've got two different things going on here. I'm saying, you know, yes, this M is a constant factor, but we don't care. We're going to ignore it. And this M is a constant factor, and we care a lot. So that feels very different, right? That feels like I'm saying one thing and the other simultaneously. That's a contradiction. And yet, the difference is that all of this communication happens in main memory, which is very, very quick. Whereas increasing M here decreases the empirical running time significantly because every disk seek you can avoid is good news. Every disk seek costs you a lot. So this analysis, different than anything you've seen, right? Normally, we'd be like, constant factors. Who cares? We're not that cavalier in this case because we're bringing in this idea of communication cost and processor speed, which are these empirical notions that are a little bit different than we've seen before. Are there questions about this? Do you have any questions about it? Yeah? Yeah, the two M's are the same number. They're the number, they are the order of the B tree. Yes, exactly. So it also is a linear function. She said, and she's exactly right, that the base of the log is really, on that lower bound, is really M over 2. It's really T, right? It's really M over 2. So in that case, I'm going, that's just a constant coefficient. We're going to ignore it. So for that piece of it, I'm going to ignore, because it doesn't tell me anything more about the structure of the problem, okay? It's M that we care about. T just happens to be half of that, okay? They're related to each other, okay? I could tell you T, I could tell you M, I don't care. We could call this, oh, you know what this argument is? This is the same argument of, do you celebrate Pi Day or Tau Day? Raise your hand if you have seen that argument. You know, so tau is 2 pi. Look, oh, never mind. Never mind. Too much. It's too much for here. But in this context, deciding whether or not we care most about T or most about M, we're going to choose M arbitrarily because that's the name of the order of the B tree. That's whoever defined these things did it in terms of M. They could have done it in terms of T as well. Then we would have had bounds that were 2T. Somebody might do that, in fact. Okay, but it's the same issue. Was there another question? I think there was another question. Yeah? Could we make it equal to N? Oh, then it's always 1. Oh, you're such a smarty. Log base N of N. Yeah, so the problem is that we are always bound by the size of our machine. So M is always fixed, right? More so than, I mean, N is bound by the amount of memory that we have too, right? So there are all these bounds, but that bound, the bound on the bandwidth, is different than the bound on the amount of memory that you have. So those are two different bounds, so we're going to keep them parameterized differently. Is that okay? You buy it? Okay. And Yeah, and we're not being particularly analytical about this constant bound, which is the bandwidth size. Just to observe that in practice, big values of m will slow down the number of disk seeks a lot. Okay, so what you should know is why we do this. Disk seeks are expensive and data is big. The definition, that's that list of characteristics of this structure. So you should be able to look at one and identify, hypothesize about what order it is, for example. And then the search algorithm that you saw and the analysis that we did today. What you don't need to know are the details of insert and delete, though I believe lab BTrees will have you puzzling over those a little bit. You should be happy if you get about halfway done with the BTrees lab. I encourage you to press on, but it does take a while. Okay, so I would like to close the book on BTrees. Is that okay? All right, let's do it. We're moving on to our next data structure, but we're still going to use this data structure to implement dictionaries. Okay, which means that we care about insert, remove, and find given a key. So keys are still of paramount importance. Our data comes along with our keys, essentially. Okay, let's see. So hash table is the data structure that we're going to talk about next. We're going to talk about it from several different perspectives. We're going to talk about it as something that we implement. We're actually also going to talk about it specifically as an interface. Now, I will tell you that when people say, oh, you just use a hash table, they're usually talking about the interface itself rather than the specific, constructs underneath the hood. So when people say use a hash table, they're probably meaning use a dictionary implemented in a particular way, not just the implementation. So there's sometimes some confusion, and there's more confusion on the next slide, which I'll tell you about in a second. Okay, so I have here a baby example, but I think it's meaningful. So these are locker numbers in a high school, say, and these are my friends. Okay, these are my friends from high school. I don't know where they are now. Okay, now my objective, I do because the magic of, so our objective is to be able to retrieve a name given a locker number. All right, so how would you implement that? If this is your objective, how would you implement it? Yes? Oh, that's way, way, way more complex. So maybe, I'll tell you, locker numbers, they look like integers to me. At my school, they were. Okay, locker numbers look like integers, and names look like strings. So actually, you are a better designer than I was intending. So given that we happen to have this data as it is, take it naively, how would you implement a dictionary on this stuff? So that when I give you a locker number, you could give me back my friend's name. Yeah? What? You could? You could. That would be way more complex. You're right. But you're going to spend 4 hours debugging yours. I'm going to spend an hour debugging mine. Okay? Because templates and compilation, blah. So you could do that. Absolutely, you could. It's probably the right thing to do. Yeah? Yeah, look at this. Who knew? I'm going to make an array like this. 0, 1, 2, 3. And I'm going to put my friends' names in there. Neil, how do you spell your name? Neil. Okay, how do you spell your name? Henry. Sorry, Henry. I should know that. Okay, you are? Derek. Uh-oh, I'm not going to spell that right for sure. N? Sean. Oh, I'm definitely. Okay. All right. So now I've got locker numbers and I've got friends. Sorry to assume that. I'm sorry. And I can get at them really easily. If I say that this is my array and it looks like that, then I can say the A in position 0 is Neil, right? Or it returns Neil. If I print it out, it is there. I can assign to it. I can remove from it. I can certainly find in it, okay? Any question about that? But what I want to observe is that we were profoundly lucky that in this pretend situation, our keys were well behaved. So what was special about them? It was that they were integers, and moreover, they were tiny. They're small integers, right? Small enough that we could use them as the indices for an array. So I'm going to tell you an anecdote because I like the memory, and it harkens back to the fact that these are my high school friends. So I distinctly remember being in high school, in our high school locker room, and like we had this commons area with lockers around the outsides, probably like you did too, and I stood there and I went like this, and I went, oh, I'm inside of an array. And so now, the next time you're at Circe or the Ark, when you're in the dressing room, I challenge you, or when you get onto an airplane, it's a two-dimensional array. Seat A19. Ah! Okay. Just ruined your life. Ha ha. All right, but of course, we're never so lucky. We've got things that are more complex. This is CS 225, right? CS 225. That isn't a smallish integer. You can imagine creating a small-ish integer out of it, but it doesn't take a very long string, like the CS part of it, to actually start creating a possible set of keys that are too big to actually use an array to cover. Okay, so that's one of the things that should be in our mind. Colors. Well, I don't know exactly how to convert colors to a small integer. I mean, maybe I do, but maybe I don't. And actually, Wade and I completely disagree on how to convert colors into smallish integers, actually what a color is. Later in the semester, we'll talk about if I give you a vertex, whatever that is, you're going to need to give me a set of edges incident on that vertex and do it in an efficient way. Vertices are not small integers, so I don't know how you're going to handle that, etc. None of these things are necessarily nicely represented as smallish integers. And by a dice roll here, I mean a K-dice roll. All right, so we have this different interface, and this is the moment I wanted to talk to you about because you will see it. We have this different interface on a dictionary called an associative array, and it's just a generalization of an array to indices of any type. So, for example, I could declare a dictionary. So we can use it for a dictionary. So I can declare a dictionary whose indices are strings and whose values are integers, for example. And the way that should live in your mind is that you still have your indices and you still have your cell values, but you think of your indices as if they are strings. Now, different languages make this interface simpler than others. Like Python wants to speak to you in this language, right? They want you to use associative arrays as the interface to their dictionaries. And in fact, they name them the same thing. Whether you say something is an associative array or a dictionary in Python, they behave the same way. And Miguel is 22. I have a question for you, though. How would you delete from such a structure? Well, it's sort of a hypothetical question, because the answer is, you know what, you might not. You may, if you wanted to delete Miguel's value, you might assign it to a canonical 0, which we might refer to as null. But removing from such a structure is you know, sort of like saying, oh, I never want to think about the 13th element of an array again. It's just a matter of interface. Okay, let's see. So I want to encapsulate, I want to capture just what our goal is for hashing so that we can hit the ground running next time. So I want to do this in sort of a mathematical way. And so I want to begin to kind of quantify things. I want to give a name to a key space, maybe refer to it as K, and let it be the description of the keys for a set of data, okay? And then, which means that every element of a set of data is going to have some key associated with it, and K is going to be the set of those things. In that case, we're going to use a function, I'm going to call it H, to map the elements of that key space to, there are a couple different ways of saying it, but I'm going to do it symbolically. You know what that is? Positive integers, but it's not a very big one. A small set of positive integers, or something from the small set of positive integers, okay? And then, of course, we'll take 0, 2, union 0. I don't know, how do you say that? Natural numbers. What's the fancy symbol for natural numbers? ZN, or just a capital N, right? Okay, fine. How about that? There. Okay. All right. So what's fuzzy about that goal? What's fuzzy is small. How big is small? And our problem is that our key spaces are often very large. So this is where we're going to pick up next time and pull this all together, formalize it mathematically and from an implementation perspective.
I was reading about this on tutorialpoint.com, so what they did was they hashed it as
For what.com?
tutorialpoint.com. They have a lot of IDs that we do data structures from there, and they said that they use modular.
Yep.